Hey guys, it's Miss Johnson here, and I'm here to finish out the 9-1 notes for you. Um, you are hanging out with Miss Klein today, and I appreciate that you are going to hear yet another video of me talking to you to get you through the rest of the 9-1 notes. Um, so we picked up in the video on number 3, and we're going to finish out 3, 4, 5, and 6 down at the bottom. So let's take a look at number 3. It says, suppose you buy a car for $15,000 and its value decreases at a rate of about 8% per year. Part A is write an exponential function for the value of the car after X years, and part B is what will the value of the car be after 4 years. So here's what we need to figure out. Number 1, this $15,000 is our starting value. The starting value in our question gives us $15,000. The other thing that we need to know, it says that this is a decreasing thing, and we know that cars in general go down, their value goes down, so we know that we're looking at a decay question. And the other thing that we need to see or take note of is the fact that that's our decay rate. So that's the rate at which it goes down. Now, keep in mind the standard form of those functions is y is equal to a times b to the x, where a is your starting point and b is your rate of change. Okay, so that's what we're going to use to write an equation for this. So here in this case, my equation would look like y is equal to $15,000. My b value would be 100% or 1 minus the 8% of 0.08. We always want to take those percents and turn them into decimals. And then the time is x, and we're talking about years here, so I have x as my exponent. Now I can simplify this. 1 minus 0.08 is 0.92, so my equation here would be y is equal to 15,000 starting amount times 0.92 to the x power. Now in part B, the second question says, what will the value of the car be after 4 years? Okay, so that means that x is equal to 4. This is my time, that's my x, so I'm going to plug it in. I get y is equal to $15,000 times 0.92 to the 4th power. Plugging that all into my calculator, I end up with a y value of about $10,745.90. Don't forget that you need to label your answer when you write those things out. A lot of these exponential functions are applications, and so they're all going to have labels in them. So I'm looking at $10,000 for my answer there. Okay, so writing that decay equation and using it with a certain value of time that we're trying to find. Let's take a look at number 4. In number 4, it says, suppose you start an experiment. You start an experiment with 45 bacteria, and they double every hour. Okay, so 45 has to be my starting point, or in other words, the A value. Doubling means multiplying by 2. That's my growth rate. Okay, and then hour happens to be my time. So writing an exponential function for this is now growing. So I have my y value is equal to 45, which is the starting amount, times the growth rate, which is 2, because I'm multiplying by 2 if I'm doubling, raised to the x power. There's my function for that. There's no way to simplify that anymore. And then it says, how much bacteria will you have after 4 hours? So now I need to take the 4 and I need to plug it in for my period of time. It's always a good idea to make sure that the period of time that they're talking about in the original question matches the one that you are asked to find, because sometimes they'll go from days to hours or from hours to seconds or something like that, and you need to convert your time somehow. So then I take the 4, I'm in hours and hours, so I take the 4 and plug it in. Y is equal to 45 times 2 to the 4th power. I can plug that into my calculator and I get y is equal to 720 bacteria. Again, don't forget to label that answer there. Okay. One more application question like this. It says in 2000, the population of Phoenix was about 1,321,045 people. It increased to 1,331,291 people in 2004. The first question says, write an exponential function that could be used to model the population of Phoenix. Write it in terms of years since 2000. Then it says, suppose the population of Phoenix increases at the same rate, estimate the population in 2015. Now, here's the problem. In part A, here's what I know. I know this is my starting value. I know that that's my A. I also know that this is the new value, the new population. Okay, new population. That's like my Y value. That's the end result. The question here is, what is the growth rate? What is B? So before we can actually write this function, we need to figure out what B is. Okay, so we're going to go ahead and see if we can do that. So now I'm going to set up everything else that I know. The other thing that I know is the time. I know that from 2000 to 2004, my time was 4 years. So that's like my X value. Okay, so now let's see what we know. I know that the end result, 1,331,291, is equal to my starting amount, 1,321,045, times some B value that I'm unsure of right now, raised to the 4th power. And I got to find that B. Okay, so let's find B. I need to first divide by that coefficient. It's a big coefficient, but it's still a coefficient. 1,321,045, 1,321,045. When I divide those two on the left, I end up with about 1.0078 is equal to B to the 4th power. Now think back to chapter 7 when we were figuring out how to get rid of that power of 4. I need to take the 4th root here. The 4th root. So I'm going to take the 4th root of 1.0078. Remember in your calculator, that's where we went to that math menu, and then we looked for the thing that looked like this. I had to put the 4 in first, then go to the math menu, put the thing in, put your value in, so on and so forth. I get a B rate here of about 1.002. Okay, so that's my B value. This is my A value, and now I can write my equation. The standard equation, because that was all just finding my B, now I got to write the equation. The equation would look like Y is equal to, starting amount, 1,321,045, times that B, get rid of this stuff, times that B value of, that I just found, 1.002, all raised to the X power, X being years. That's my equation. So I was given the starting, I was given the ending, and I knew how much time had passed. I had to solve for B first. Then I could go back and write the equation. Now I can use that equation to estimate the population in 2015. 2015 minus 2000, which is my starting value, is 15. That means that's what I'm going to plug in for X. So I'm going to take that equation that I wrote in A, Y is equal to 1,321,045 times 1.002, all to the 15th power. And when I plug that into my calculator, I end up with 1,361,236 people. Okay, again, label your answers. These are all applications. Okay. So that's just using the exponentials there and seeing if we can figure out how they match each other. Last example down at the bottom, number 6, is just solving an exponential equation. Now here's the thing about the exponential equations. If I'm looking at two sides of an equation and I know that their bases are equal, as they are in part A, 3 is equal to 3, that means that their exponent must equal the other exponent. So that's what I'm looking at here. In part A, I can take 2n plus 1, set it equal to 4. I'm going to subtract 1 from both sides. I get 2n is equal to 3, and divide by 2, n is equal to 3 halves. Okay. The way you can check it is take it and plug it back in for n. If I took it and plugged it back in for n, I get 2 times 3, which is 6. 6 divided by 2 is 3. 3 plus 1 is 4, and I'd end up with an exponent of 4. Okay. Let's take a look at part B. Now in part B, our bases don't necessarily look the same. So let's see if there's a way that we can fix those bases so that they are the same. The base on the left appears to be 2. The base on the right appears to be 8. So let's see if we can figure out how to fix that. I know that I can put these powers together. That's going to help me right off. So I know that I can make that 2 to the 4x power. The other thing I know is that I can take this 8. This 8 is the same thing as saying 2 to the third power. Okay, well there's my common base. So I'm going to have 2 to the third power raised to the x minus 1. And now I can, using my power of powers property that I used over here, multiply these. This is going to be distribution. So I have 2 to the 4x on the left equaling 2 to the 3x minus 3 on the right. Now I have the same base. Now I have exponent equaling exponent, and I can solve. So I'd have 4x equals 3x minus 3. I would subtract 3x. I'd get x is equal to negative 3. So that's my value there. And then one more example, and again in part C, they don't necessarily look the same, but let's see if there's a way that I can make them look the same. So the base on the left in part 3, or in part C I should say, is 4. Base on the left is 4. Get rid of that. And the base on the right, it's kind of hard to tell. The base on the right, who really knows what it is, but I know I have 1 divided by 64. Let's see if I can get that 64 out of the denominator, because with the fact that it's in the denominator is not helping me. If I wanted to take 64 and move it back up to the numerator, that means I would have 64 raised to the negative first power. Okay, that puts it back up in the numerator. And we know about those negative exponents, moving them up and down, changes them from negative to positive. So now I'm at 4 to the 2n minus 1 is equal to 64 to the negative first. Getting closer. Now I have no fractions to work with. Now, is there a way that I can write 64 so that it has a base of 4? Well, yeah, I can, and this is where you can use your calculator to help you. But if I plugged into my calculator 4 to the third power, 4 to the third power is 64. So I can keep the 4 to the 2n minus 1 on the left, and I can change 64 on the right to 4 to the third power, and remember that's all raised to the negative 1. So this has we have a lot of properties of exponents in this lesson that we're reviewing. Then I can multiply those together because power of a power means multiply. So 4 to the 2n minus 1 on the left and 4 to the negative third on the right. Now I have common bases, exponents equal to each other. 2n minus 1 equals 3, add 1, 2n equals 4, divide by 2, and I get n is equal to 2. And again, a way to check your answer is to go ahead and plug that in. If I plugged that in, I would have 2 times 2 minus 1, and I could figure out if that's going to give me the right power or not. Okay, so that's going to be the end of our notes for 9.1. Thanks for listening, and good luck working on your worksheet, and I will be back on Monday, and we'll go from there. Have a good weekend.